So good afternoon and welcome to today's energy seminar. It's the last energy seminar of this academic year. I'd like to first take the opportunity to thank my partners in crime, the ever resourceful Rachel Madison, our pre-court program coordinator, and the almost equally, or perhaps on certain days more resourceful, CA for the class, Noel Eveland, who's up here. And finally, since he's standing right behind me, I'd like to thank the pre-court director, Will Chua, who actually has supported us in many ways and many times all during the quarter. And with that said, I'd like to once again ask Will to introduce our very august big celebration at the end of the year, the ultimate cleanup hitter for this year. So Will, take it away.
Well, John, thank you very much. And there's still plenty of seats up front. Please come forward. I understand that this is the extra lecture, but I'm so delighted to see this wonderful turnout to hear from Emory Levin. So before I start, I just want to acknowledge Holmes really quickly. Holmes, thank you very much. And Holmes has kindly pulled together a few slides that will barely, I think, do justice of Emory's many accomplishments. And I think it's been many years since I have used slides to introduce someone. And I'm really glad to do this for Emory. So often we would say someone and introduce someone as a national treasure. And I think for Emory, I shall introduce him as a planetary treasure. We are really delighted to have him here today to talk about energy efficiency, renewable energy, and of course, sustainable design. So the few slides here chronicles Emory's journey for his career and also here at Stanford. And if you take a look at this seminal paper, which got things started, was back in 1976, written in the Foreign Affairs. And that really got the discussion on energy efficiency going here in the United States and in the rest of the world. And this led to the very famous picture there with a slightly younger version of Emory speaking to President Carter. And Emory's journey started and landed at Stanford actually very early. In 1978, he addressed a packed auditorium in the Turman Auditorium just 2 years after. I'm sorry? That's your seminar series, Sir John. All right. So you're giving away your age here. And to give you a sense of the time, you know, this was the prevailing technology of the time. I think those are HP calculators for advanced computation. So, you know, this really initiated the relationship and the special relationship between Stanford and Emory in 1978. And if we continue to fast forward, in 1980, Emory published this extraordinarily influential treatise on system thinking. And as of late, myself have also really embraced this system level thinking to complement many of the bottom-up technological solution and complement it with top-down thinking to bring the system together. The question that Emory really focused on was, can we use less energy to get the surfaces we want, focusing on energy demand rather than supply, or in addition to supply, as the way to really approach the energy challenge here. Keep fast forwarding. We continue to intersect Emory. 1995 here, he was giving the Guggenberg Lecture at the Graduate School of Business. And here, and then he launched the Rocky Mountain Institute as the Think and Do Tank, now known as RMI, which he served as the chief scientist until 2019, and of course remains today as chairman emeritus and trustee. And this is really an exceptional team of people that work toward an energy future across buildings, manufacturing, mobility, and much more. Emory has been recognized with many honors and also seeing opportunities before they become mainstream. And here are just a couple of important publications from Emory, but the one that I got really excited by was he saw data centers coming way before data center became the trend that it is today. And these type of leadership is exactly what we need. This is 2003. So this is 22 years ago. And today we're talking about how exciting data centers are in terms of energy demand. This was recognized by Emory more than 20 years ago. There are many more recognitions, too many to go through. One of the most impressive prizes that Emory has received is the MacArthur Genius Fellowship, recognizing his contribution to integrated design. And many honorary doctorates, I think 12 of them in total, teaching at 10 plus universities, including Stanford, of course. And the journey continues. At Stanford, we were fortunate to have Emory return in 2007, again, to packed crowds. I was told by Holmes that this was during spring break in 2007. And he not only had one packed crowd, was 4 consecutive packed crowds during spring break. And we know how hard that is. And today's crowd here, I think, is a testament to the type of people and convening that Emory can bring together. And we're also very thankful that Emory contributes to our teaching here at Stanford with courses on energy efficiency, working with Joel Swisher, and teaching still today in this very quarter. I believe your class have finished up as well on Wednesday. And introducing these important concepts to all of our students and aspiring energy practitioners as well. And at the Precourt Institute, we are honored to host Emory as a distinguished visiting scholar, and to also partner with him not only on education on campus, but also on mobilizing the rest of the world with the recent launch just a few months ago on the Energy Learning Hub to look at integrative design for radical energy efficiency, to make sure that this important content is accessible to the world. And today, we are glad to have Emory back yet another time to share with you how we might increase the global energy efficiency by 5-fold through integrative design. Please join me in welcoming Emory Lovins to the stage. Emory, thank you for your leadership.
As somebody said after that kind of introduction, I can't wait to hear what I'm going to say. Well, thank you for the honor of summarizing how to use delivered energy 5 times more efficiently by about 2060, or about 3 times more efficiently by about 2040. Engineers might want to call that 5-eta. It can make the energy supply side of global climate protection half as hard as it looks today when we're exploiting less than half the solution space. Raising end-use efficiency by several-fold more than normally assumed needs no magic, no miracle, not even new technology. It needs beginner's mind, whole system thinking, rigorously simple design, meticulous attention to detail, and then to get it implemented, gentle diplomacy and relentless patience. I'll sketch how integrative design can optimize whole systems for multiple benefits to achieve radical energy efficiency in all sectors. This proven practice, which Joel Swisher and I teach, applies orthodox engineering principles, but asks different design questions in a different order. It's the most overlooked part of the energy revolution that is rapidly shifting the world from inefficient to efficient use, fossil fuels to renewables, fuels to electricity, and centralized to distributed resources. 4 things going on at once. The result is the current tipping point. The world's total use of fossil fuels roughly peaked about 6 years ago. and began bumping along a plateau with minor excursions due to weather or war. Right around now, carbon-free power is starting to meet all demand growth and more, even as electricity replaces more fuels, all tipping fossil fuels into steepening decline. So the light gray and dark gray existing trends in net zero scenarios shown at the far right are from Bloomberg New Energy Finance last year, but were similarly framed by the International Energy Agency, BP, Shell, McKinsey, Rystad, and others. And they all say the trend of the previous 2 centuries is now starting to reverse. So the burning of fossil fuels will now begin to fall ever faster. Indeed, China's carbon emissions just peaked, mainly because nearly half its new cars are electric, and China met its 2030 solar and wind target last summer, 6 years early. At least in the U.S., this transformation has not been mainly driven by public policy or climate concern. Instead, it's chiefly business-led, market-driven, informed by energy security and industrial opportunity, and similar to many classic cascades of technology disruptions triggered by innovation and motivated by profit. Kingsmill Bond's team at Emper frames it as the electrotech revolution with 3 synergistic technology clusters, but that framing includes only about a third of the total energy efficiency opportunity. Here's how, in 3 columns. At the upper left, thermal power stations' huge conversion losses in red are eliminated at the lower left when solar and wind power in green generate directly without a steam cycle. In the middle column, fuel combustion at the top provides heat severalfold less efficiently than a renewably powered heat pump concentrating free low temperature heat. And in the right column, gasoline and diesel engines with their big losses in red are far less efficient than renewably powered electric motors in battery electric vehicles. So across the bottom row, replacing fossil fuels with renewable electricity is 2 or 3 times more efficient in turning primary energy into final energy or delivered services. And that shift could save the world nearly $5 trillion a year. But it does not yet include higher efficiency in the equipment being powered, or the building being heated, or the vehicle being moved. That end-use efficiency, my topic today, makes the heat pumps, motors, EV batteries smaller, cheaper, less mineral intensive. Both these kinds of efficiency multiply to form primary energy efficiency. And most of its potential is in the end uses, where global efficiency can profitably rise by about 5-fold, roughly twice the upstream savings. Thus, focusing just on the upstream savings omits roughly 2/3 of efficiency's total potential, as I'll explain. The International Energy Agency says that energy efficiency, now employing nearly 10 million people, has delivered half of the past 20 years' global decarbonization. Its pace must now double to 4% a year to reach net zero by 2050. IPCC's finding that efficiency can deliver 40 to 70% of future decarbonization is understated because it includes only technology and policy. And I'll sketch how innovative design and new business models can make that efficiency resource severalfold larger and quintuple end-use efficiency by 2050 at a pace that is within the Aquabar's IEA's forecast range, and that's not a limit. By the crude method or metric of primary energy per dollar of GDP, saved energy is the world's biggest energy source. Worldwide, just the energy saved since 1990 supports more energy services than oil does. Over 70 years, increased energy efficiency or energy productivity enabled 2/3 of U.S. energy services and 3/4 of their growth. Yet that barely scratches the surface of how much end-use efficiency is available and worth buying because the efficiency resource is not static. It's highly dynamic. A little history. Around 1975, U.S. government and industry all said that the total input energy needed to make $1 of real GDP could never drop. A year later, I heretically suggested it could drop 72% over the next 50 years. In the first 49 years, it's dropped 65%, despite frequent federal and incumbent hostility. The hydrocarbon industries just outspent the clean energy industries by 27-fold to influence current energy legislation. Yet, just the efficiency innovations already added by 2010 can save another 3-fold twice what I originally thought, at a third the real cost. And today that's looking conservative, because optimizing buildings, vehicles, and factories as whole systems, not as piles of isolated parts, can often make very big energy savings cost less than small or no savings, turning diminishing returns into increasing returns. When saved energy, about two-thirds due to smarter technologies, dropped U.S. energy use by 65% so far, the cumulative savings were immense. Renewables, meanwhile, nearly tripled, but with 27 times less cumulative impact. Who knew? Renewables get virtually all the headlines because they're visible. But energy is invisible, and the energy you don't use is almost unimaginable. Worldwide, renewable electricity generation in green has zoomed past nuclear in magenta, gas in blue. This year it should pass coal in white. And modern renewables now look set to add more generation in 5 years than in the past century. They've also shifted energy from fuel extraction economics, the more you dig, the more it costs, to equipment manufacturing economics. So the more you build, the cheaper it gets to capture free sun and wind. And already the cost curves of fuels and renewables have irreversibly crossed, triggering that green curve's exponential growth. As Tom Friedman says, the more we buy, the cheaper it gets, so we buy more, so it gets cheaper. So market competition will do many fuel-based incumbents, but we're largely overlooking here efficient use, a comparable or bigger energy resource that may also be deployable quickly. What could more efficiency plus renewables do together? In 2011, 60 colleagues and I documented in a business and design book called Reinventing Fire how to triple U.S. energy efficiency and quintuple renewables by 2050, reaching that era's 2-degree climate target $5 trillion cheaper, all led by business for profit. How's that doing in the marketplace? Well, as these charts show, the first 12 years of that 40-year journey are pretty well on track, green actual versus blue proposed. I think largely because the private sector smells the $5 trillion on the table. That's exactly what should be happening. Our book's translation, meanwhile, inspired China's NDRC strategy agency to lead a rigorous 2017 government study showing how to cut China's carbon intensity 13-fold. Its advisory committee then wrote the 11th Five-Year Plan's energy strategy. The rest is history. For comparison, Reinventing Fire's U.S. synthesis derived 2050 electricity use 2 to 4 times lower than Princeton's Net Zero America study assumed. Yet, our quadrupled electric efficiency cost 10 times less than the retail electricity it saved, so we should have bought far more efficiency. So how can integrative design make energy savings several-fold bigger, yet cheaper? It's less by adding more technologies than by designing them out. It uses not more but fewer devices, not fancier but simpler devices, more artfully chosen, combined, timed, and sequenced. And those granular devices can be mass-produced with rapid learning, just like renewables. Familiar resources like copper ore bodies and oil reservoirs are finite and depletable assemblages of atoms. But energy efficiency resources are infinitely expandable assemblages of ideas, depleting only stupidity, a very abundant resource. Let me give a few examples. My wife Judy and I live near Aspen, 2,200 meters above sea level. Outdoor temperatures used to dip as low as minus 44 C with up to 39 days of continuous midwinter cloud, but our house does no combustion. That's so 20th century. Super insulation, ventilation heat recovery, and super windows that insulate like 16 to 22 sheets of glass, but look like 2 and cost less than 3, make it 99% passive solar heated, 1% active solar. Eliminating the heating system subtracted more capital cost than efficiency added. So total construction cost went down. Saving also 90% of the electricity, 99% of the water heating energy, and half the water did add cost, but all the savings combined paid back in 10 months. Today that would probably be less than zero. The central atrium, shown here in a February snowstorm, has so far produced 83 passive solar banana crops. Without needing to look like this, our house helped inspire several 100,000 European passive buildings. An analogous approach worked fine in steamy Bangkok, Nearly everyone on Earth lives in climates between Bangkok's and mine. Integrative design gives many benefits from each expenditure. So the white arch in the upper middle there has 12 different functions, but only one cost. Or in a hot, dry climate, this integratively designed and needlessly ugly tract house in the Central Valley achieves superior comfort with no air conditioner. PG&E figured that if built in a mature market rather than one-off, this quintupled efficiency design would have cost less than normal to build and to maintain. Here on the Stanford campus, the Carnegie Building's passive system delivers excellent comfort at normal cost with energy use about a fifth of code. And it would have saved half its remaining cooling energy if Peter Rumsey had been allowed to design the cooling system too, the pumping system. Progress in office buildings is illustrated by a series of green energy intensities and yellow savings scores. So RMI's integrative design to retrofit the Empire State Building saved 38% of its energy, later 49%, with a 3-year payback, because smaller mechanicals paid up front for most of the efficiency. Now the owner hopes to raise the savings to 80%. A major energy service company also offered a 3-year payback, but with disintegrated design, saving 6 times less energy than we did. 3 years later, our cost-effective Denver retrofit saved 70%, making this half-century-old federal complex more efficient than what was then the best new U.S. office, which in turn is only a third as efficient as RMI's passive net positive no mechanicals office near my home, using 1/9 the normal amount of energy. And this Bavarian building uses 2/5 less energy than that. Yet these technologies all existed over a decade ago. What mainly improved is not so much technology as design, the way we apply technology, how we put the pieces together. In 6 muggy Indian cities, 1.5 million square meters of integratively designed offices use 80% less energy than the Indian norm, with 10 or 20% lower construction cost. Yet superior comfort and satisfaction. Glare-free lighting is delivered throughout by contract. If workers complain of glare and demand blinds, the architect doesn't get paid. IPCC disproved diminishing returns assumptions by graphing decade-old data showing cheaper energy savings toward the right and cheaper energy savings toward the bottom and bigger energy savings toward the right. For diverse building types and European climates, the best new builds on the left and retrofits on the right saved up to at least 90% of their energy without costing more per unit of saved energy. The vertical cost scatter shows the business opportunity to conform inferior projects to best practice. Recent super-outsolation retrofits to net zero using the Dutch Energiesprong method, like adding a tea cozy around your house, are also proving economic without subsidy. And when an old Chicago office tower is doing a routine window replacement that saves nothing, a simultaneous deep retrofit could cost even less and quadruple efficiency. Here's the next game changer. A Princeton experiment kept Singaporeans comfortable outdoors in a shaded, open-ended pavilion without drying, cooling, or substantially moving the hot, humid, still air. People were instead cooled radiatively by absorbing far-infrared radiation from their bodies into vertical panels circulating 17-degree water separated from the humid air by plastic film. Panels cooled to 23 to 25 degrees can thus deliver thermal comfort on a 32-degree day with 80% relative humidity. The water can be passively cooled by special surfaces that radiate infrared to the sky in any weather. Combining these passive technologies may provide tropical climate comfort in new or old buildings or in vehicles using no or almost no electricity. A snap-together plastic version might even be cheaply retrofittable into the world's apartment blocks and slum dwellings. Let's go try it. It may virtually eliminate long-term growth in the world's peak demand for electricity. What are we waiting for? Inside buildings are other surprising opportunities. For example, this fist-size heat pump can deliver 6 to 15 units of hot water per unit of electricity. This electric induction cooking system with vacuum-insulated pots is several times more efficient than induction and otherwise superior. In industry, which uses half the world's energy and electricity, the same methods apply. For example, Paul Westbrook and I co-led the design of this Texas Instruments semiconductor wafer fab to use 40% less energy with 30% lower construction costs. So it was built in Texas, not in China. It inspired cutting company-wide chip-making energy intensity by 70%, water 62%, greenhouse gases 72%, with further gains to come. RMI's next wafer fab design showed how to save about 2/3 of the energy use and half the capital cost, while replacing all 22,000 tons of chillers with any of 3 natural cooling methods that can yield upwards of 100 units of cooling per unit of electricity. Across diverse industrial sectors, RMI's $60+ billion worth of redesigns typically found about 30 to 60% energy savings on retrofit, paying back in a few years. Far better than the orange zone in the upper left, where most energy service companies deliver disintegrated design. In new builds, 40 to 90+% savings generally had lower capital costs than normal. And these superior results come from rethinking industrial processes and from redesigning basic elements like pump and fan and motor systems. You see, half the world's electricity runs motors, and half the motor torque runs pumps and fans. Engineers focus on those devices' efficiency, but they often seem to forget that better pipe and duct design can save 80 to 90+% of the friction, 97% in my house. If everyone did that, it could save roughly 1/5 of the world's electricity, or half the coal-fired electricity, typically paying back in less than a year in industrial retrofits and instantly in new builds. In pipes, friction drops as nearly the 5th power of diameter, but cost rises as only about the 2nd power of diameter, so we should use big pipes and small pumps. Fat, low-friction pipes make the blue pump on the right so tiny it looks like a decimal point error. And you notice it's raised up to meet the pipe rather than dipping the pipe down to a pump on the floor, then back up using 4 elbows. The 10 chillers, normally in a neat row, are staggered to eliminate remaining elbows when we lay out the pipes first, then the equipment. We lay out supply pipes as if they were drains. We bend minds, not pipes. Yet such rearrangement of designers' metal furniture remains largely unnoticed and unpracticed. Not yet in any standard engineering textbook, industry forecast, government study, or climate model. Why not? Because it's not a technology. It's a design method. And few people yet think of design as a path to speed and scale. Probably no climate models even compete or compare efficient use with more supply. What do such savings mean for those pumps and fans that use over 1/4 of the world's electricity? Well, from the fuel burned in the power plant to the end use, many successive losses compound, so only 1/10 of the energy in the fuel comes out the pipe as flow. But now turn those compounding losses around backwards from right to left, and every unit of flow or friction you save in the pipe saves 10 units of fuel cost, emissions, and global weirding back at the power plant. And as you go back upstream, the components get smaller and cheaper, reducing total capital cost. So always start your savings downstream. Start at the end. Start with intent, with purpose. Do you even need the flow? Passive buildings and equipment will need less or no pumping. And as you make the motor systems 5 or 10 times smaller, adding 35 drive system improvements, of which you pay for just 7, can raise the potential energy savings from 1/5 to 1/3 of the world's electricity. That's not in the climate models either. Now let's apply the same logic to big old data centers. 2/3 of the fuel fed into the power plant is lost at the plant and the grid. Half the metered electricity is then lost in the cooling system and the uninterruptible power supplies before reaching the servers. Half the server energy doesn't reach the chips because it's lost in inefficient, usually very underloaded power supplies and many superfluous fans. Next comes severe underutilization of computing resources, partly through insufficient virtualization. The resulting energy flows about to vanish, so let's magnify it. Next comes sloppy bloatware, running many unnecessary threads and processes, and making simple tasks complex because compute cycles were cheaper than programmers' attention, and someone else bought the energy. Downstream of all that, you may even have inefficient business processes. So in all, the red numbers across the bottom reveal that just a few hundred thousandths of the original fuel energy actually delivers customer value. Where should we start fixing this? Downstream. First, write elegantly terse code, optimally compiled, with the goal that every compute cycle is a needed and wanted one. I had assumed this could save about 1 order of magnitude in compute cycles, but recent tests found 2 orders of magnitude. And the shift to mobile devices now makes efficient code valuably stretch battery life. Then at least quadruple server efficiency, now even more. Other servers will need far less cooling and power supply, both doable in smarter ways. And we could even save half the utility losses by using fuel cell trigeneration, cheaper than the UPSs it displaces. So multiplying these savings from downstream to upstream cuts total energy use by at least 2 orders of magnitude. When we made this diagram in 2009, our client rejected most of our recommendations. So very disappointingly, we were only able to triple efficiency at the same capital cost. But our partner EDS said that had our recommendations all been adopted, we would have saved about 95% of the energy and half the capital cost. In today's far larger AI data centers, my new essay at ai-electricity.stanford.edu called Artificial Intelligence Meets Natural Stupidity, Managing the Risks, explains how better hardware, software, and system architecture are together quadrupling system efficiency each year, with, Bill Joy says, about 1 million-fold to go. Wonderful new kinds of low or zero or negative carbon cement are emerging. So are smart ways to use less, cooler, and cleaner process heat, including solar. But what should we do first? Start with demand. Need less, use other, use less, use longer, use again. Align incentives. Only after minimizing need should we be redesigning production. There's scattered but strong literature showing how smarter structural design and new business models can profitably save at least half the world's cement and steel that now release 15% of global CO2. Better specification and application of concrete can save another factor too, so together saving 3/4 before adopting lower carbon materials or production processes. Better structural design takes many shapes. Substituting tension for compression structures typically looks better, costs less, and uses about 1/8 the tons. Pouring concrete into curvy fabric forms, not rigid prismatic forms, could often save over half the concrete by putting strength and stiffness only where they're needed, and then the weight savings compound because you need less strength to hold up less weight. An airy dendritic 3D printed bridge can carry mainly its users, while massive concrete bridges support mainly their own weight. Here's a 3D printed stainless steel bridge. Most importantly, floor slabs are about half the total weight of a typical mid or high-rise building. A 5-centimeter thick concrete floor slab, corrugated like this one, can replace a 30-centimeter thick flat slab, cost less, and save 3/4 of the cement and all the steel. Thin floor slabs plus passive energy design can then save a further 15% of core structural materials and 3/4 of the energy in a new mid or high-rise building like the Singapore one at the upper right, while increasing net rentable space by a stunning 55%. How? Well, designing out a vertical meter of mechanicals at each story, plus thin slabs, can fit 3 stories with normal 2.8 meter ceiling height into the current height of 2 stories. Cost, complexity, and time fall dramatically. What about transport? 2/3 of the energy needed to move a typical car is caused by its weight, and only about 0.3% of the fuel energy actually moves the driver. Ultralight, ultra-strong materials can slash energy use and improve crash safety. BMW made money on each of 250,000 i3 electric vehicles, including mine, by making it out of costly carbon fiber paid for by needing fewer batteries to propel the lighter weight car. Fewer batteries also recharge faster and need less electricity and infrastructure, potentially saving the U.S., says EPRI, $200 billion a year. The saved weight snowballs spectacularly. Assembly saves 2/3 of the normal capital and water and half the energy, space, and time. It also eliminates the conventional body and paint shops. It's much better for workers. The car's quadrupled efficiency is uncompromised with many driver advantages. This and 14 other empirical examples show that the design space for efficient automobiles is at least 3 times bigger than officially assumed. Ultralighting can also save up to about 2/3 of the scarce battery minerals. Then 5 other multiplicative forms of efficiency could manage the rest. Meanwhile, Bloomberg New Energy Finance reports that China's strategy for its 2030 flagship cars includes carbon fiber structures, displacing 4/5 of their iron and steel. Watch this space. Next come a couple of hypercars, both from firms I advise, that are 2 or 3 times more efficient still, say more than a Tesla, and ready to enter volume production as soon as they finish raising capital. Most drivers will not need to recharge this composite 2-seat 3-wheeler in which I just invested, or this Dutch 5-seat 4-wheeler, because their topside solar cells capture enough energy to power ordinary daily driving without recharging. Tesla's battery electric heavy truck is being customer tested for mass production starting around the end of the year. It'll triple to sextuple the fleet efficiency of Class 8 trucks with great economics. And this thoroughly flight-tested air taxi from Southern California could fly nonstop from San Francisco to, say, Dublin, Ireland, with 1/8 the fuel use of a business jet. A mid-size hydrogen model has been announced, plus, importantly, a transonic business jet for 2030 service with doubled efficiency and cabin size. The superlaminar aerodynamics can scale to probably 737 size and could blow up aviation's business models. Or metal aerostructures could be replaced by 98% lighter polymer lattice structures. Other proven improvements may let my grandsons fly all-solar airliners across the Pacific. My annual Explore Energy House lecture for Holmes last month on fossil-free flight used this logo. Turns out the pterodactyl had the last laugh, because then I learned that extinct pterosaurs, the biggest flying creatures in Earth's history, had wingspans around 10 or 11 meters, 3 times that of today's biggest birds. Their bones had paper-thin walls stiffened by internal struts and complex porosities. Paleobiomimicry applies such designs from 1/6 of a billion years ago to improve today's aerospace structures. Practically anything people can design, nature already designed better, so biomimicry greatly strengthens the promise of integrative design. Some big companies paying attention sustained 6 to 16% energy savings for years. So why is the world now saving energy at only about 2% a year, not twice that, or faster? Well, energy efficiency gets little attention and respect for at least these 20 tedious reasons, plus specialized ones in each end-use sector. Our class takes about 2 hours just to list these obstacles and their effective solutions. Each one can merit a whole seminar. We can't do that here. But in general, these are not the familiar obstacles or solutions that policymakers got good at with renewables. They're a new set of barriers and opportunities in different scales and contexts, requiring similar insight, tenacity, innovation, and entrepreneurship. Most of efficiency's practical needs are systematically neglected because few policymakers realize the prize is far bigger, yet cheaper than they thought. Demand-side decarbonization is usually cheaper and may well be faster than supply-side, especially if we can spread integrative design by images, means, social media. Efficiency's risk portfolio is more diversified than those of wind and solar, with more workarounds, more ways to evade obstructions. Efficiency can be more pervasive, bottom-up, granular, accessible, equitable, benign. That's all good. It deserves our attention, skill, priority, and juice. Through practical design exercises, our students build their skills in applying these 10 principles or pillars of integrative design. These habits can rewire your brain and make you lastingly more original and effective in whatever you do for the rest of your life. So integrative design can radically save energy and water and materials across the whole economy, in every sector and nearly every use. The examples I've given from hundreds in our course illustrate that potential. But what can it add up to? Well, this rough summary shows the immense end-use energy potential for efficiency, not counting the threefold prior potential from switching to primary renewable electricity. This is end-use only. And yet it is seldom recognized, taught, delivered, expected, or rewarded. Why? Well, observing buildings, vehicles, factories in over 70 countries in 50 years, I see the same design errors repeated everywhere because they're widespread in our textbooks and our classrooms. So I'm hatching a plot for, well, to put it a mite impolitely, the nonviolent overthrow of deficient engineering. Teaching disintegrated design condemns our descendants to perpetual retrofit of inefficient stuff, not a worthy legacy. To help us be good ancestors, I'm seeking fellow students, teachers, practitioners to collaborate on making integrative design shift swiftly from rare to common. I'd like to help gently retread in-practice design professionals and the skilled tradespeople like pipe fitters, sheet metal workers, mechanical contractors who informally design many systems. I'd like to help improve design software to allow and coach integrative design, to find iconic CEOs to apply 5-eta in their firms and proselytize their peers, somewhat as Jack Welch did with Six Sigma. Partners in India, Australia, Sweden just hosted my Teach the Teachers course to improve our pedagogy together. Our Stanford course has now been refined in 14 iterations. And now I'm eager to test all 20 or so known scaling vectors, see what works, and start scaling to make integrative design as common as grass. That work should start here and now. Then we won't need speculative, slow, costly technologies like nuclear fusion and fission, except, of course, the well-engineered and remotely sited free fusion reactor already thoughtfully provided and cheaper to harvest than to replicate. And if anything I've said has surprised you, just remember Marshall McLuhan's remark that only puny secrets need protection. Big discoveries are protected by public incredulity. Let me end with a top-down reality check. A Cambridge team found global energy use in 2005 was only about 1/9 as efficient as physics allows. So, including passive options too, they found that, they said, about 85% of energy demand could be practically avoided using current knowledge and available technologies. Well, adjusting for 2 decades of savings since then leaves about 5-fold today in untapped second law efficiency gains, consistent with my bottom-up 5-eta. Meanwhile, new learnings have raised Allwood's 85% practical potential to nearly 100%. So techno-economic potential is converging with theoretical potential. Whatever the right number is, it's the integrative design gets us closer, deeper, cheaper, faster. It expands by severalfold, a resource that IPCC already considered to be about half the climate solution. So it's time we turned it from a rarity into standard practice and built it into our models, policies, pedagogy, research, and investments for speed and scale. Then the revolutions in renewables, electrification, decentralization, even digitization and democratization can get faster, cheaper, and easier. The Durr Schools and Precourt Institute's leadership could now prove decisive. We all know why this is urgent, and I invite you to hold these two seemingly contradictory thoughts at the same time. Happily, while climate science models conservatively understate the speed and the runaway potential of climate change, models of climate choices and consequences, at least as conservatively, are understating what we can do to slow, stop, and reverse climate change. Offsetting these two contrary biases, the race of our lives, the race for our lives, is very much on. The outcome is up to each of us, and despair and complacency are equally unwarranted. Our responsibility is to enable the new energy system, not protect the old. So the energy transformation can move at the pace and cost of design and software, not of infrastructure, and can be not constrained by the inertia of incumbents, but sped by the ambition of insurgents, like many of you. So go forth, be fruitful, and subtract. Thank you. I'm eager to learn what's on your minds.
Emery, we're grateful for your leadership and also the call to action here. We have time for a number of questions.
I'm sure I said nothing controversial. And here's another mic.
Hi, thank you so much for sharing your wealth of knowledge with us today. I wanted to learn a little bit more about those reasons that end-use efficiency gets little attention.
Sorry, about?
The reasons that end-use efficiency gets little attention. Can you go into detail about maybe what are the most salient reasons or that you find that integrative design doesn't get as much attention as it should?
Well, most people don't realize that they can do it and don't know how to do it. I'll just put this up again as a little eye candy. There are thousands of obsolete codes and standards, which sometimes even prohibit doing the right thing. It's a very granular, distributed resource that doesn't tend to attract rent seekers and those seeking political credit. In most of the United States, state regulation rewards utilities for selling more energy and penalizes them for cutting your bill. We do know how to fix that. California has. Most of the suppliers don't like it and portray it as privation, discomfort, and curtailment. Most energy users have very high implicit discount rates, and they think efficiency is binary. It's like a garage, either a house has it or it doesn't, instead of a rather dynamic spectrum that keeps evolving. There is the perfect markets myth that if this were worthwhile, it all would have happened already. And that's what came up in '76 with that Foreign Affairs article. Some of the top energy economists in the country said, oh, if any efficiency were worthwhile, we would have done it already because we and supposedly everybody in the world lives in a perfect free market. Well, no good economist would claim that for long. We reward designers for what they spend rather than what they save. We tried reversing that. It works really well, called performance-based design fees. Most of our training is obsolete. Much of our official information is outdated or wrong. And this stuff moves really fast. It's very diverse. You got a slight glimpse of that, but there's layer upon layer underneath that is really hard to keep up with, even if you're specialized in it. And most executives, unless you're in a business like aluminum smelting, don't pay a lot of attention to minor factor inputs compared to stuff like labor. There are huge side benefits to efficiency, often one, sometimes two orders of magnitude, that are usually not counted. And we're many billions of dollars a year into creating efficiency industries that will try to come sell you efficiency, but mostly they're not selling this kind. They're selling fragmented, incremental, disintegrated design and just installing equipment, not paying much attention to design. There isn't nearly enough marketing to build understanding of what's possible, and almost nobody teaches it. I mean, here at Stanford, we have, hundreds of people doing wonderful work on energy. It's 98, 99% supply side. We need to rebalance that portfolio. So that's a little list to start with. We could elaborate it.
In the back.
This is an amazing presentation. Thank you so much. I was curious about the slides on reducing the weights of manufactured cars to improve energy and materials efficiency. Does that result in any differential impact between a lighter carbon fiber car and a more traditional heavy chassis upon collisions or accidents? I remember when I was 16, I drove the heaviest car in the household because that was touted to be the most safe in any sort of collision. I'm curious on how this.
Yeah. Well, for decades, our National Highway Traffic Safety Administration used a database that was interpreted in a way that conflated size with mass. It turns out when some more careful analysts teased the two apart, you got the opposite answer. It turned out that what was protecting you was not weight but size, crush length. And if you use materials that are light but strong and absorb a lot of energy per kilo in a crash, then you can make the vehicle bigger if you want, more comfortable, have more utility, without making it hostile and inefficient. So you can end up saving lives, oil, climate, and money all at the same time. Eventually, some of us were able to persuade the head of NHTSA to look carefully at this, and he happened at the time to be an ER room physician who dealt with a lot of car crashes. So it was important to him. And when they looked carefully at it, they changed the policy so that U.S. Auto and light truck safety standards are now based on size measured by footprint rather than by weight as they used to be. So the two are decoupled, and there's now an incentive to make your vehicles lighter but stronger. The main reason that things like the carbon fiber structure I showed for BMW i3 have not taken over is not technical or economic, it's cultural. It's really hard in something as complicated as the auto business to change how you design and build everything. That's why the China strategy is so interesting. If they actually follow through with that, that could flip the whole industry.
Thank you.
Take one more question, Sally.
Okay, thank you. So question, is this on? There we go. If you were to look at universities around the world or regions of the world where you think they come as close as possible to your vision of what we should be teaching people, what are those institutions and where are they located?
It's more individuals than institutions, and they're really scattered. For buildings, I'd say you probably go mostly to the Nordic countries and Netherlands and Germany. For industry, maybe Sweden, Switzerland, Germany. Vehicles, I'm not quite sure where it would be right now, but could well be the U.S. That Aptera I showed that I can't resist mentioning the total air drag of that teardrop-shaped two-seater is less than the air drag of the side mirrors on an F-150 pickup truck. There are not nearly enough people doing this, and that's why I'm doing several Teach the Teachers courses every year. So the one I just did in Chennai is supposed to spread to 3,000 technical higher ed institutions across all India. Let's see if that works. But we have a lot of work to do, and we need to get our own house in order and really focus the extraordinary leadership Stanford can bring to this field.
Emery, we absolutely agree. More should be done here at Stanford on energy efficiency, and we will.
Thank you.
Emery, please join me in thanking Emery one more time.